Nurul, boleh panggil Nurul ke?
Saya Nurul.
Kat mana nak klik
Nak
share?
Ada button tepi mic tu, ada button macam gambar screen PC.
Oh, dia tutup. So tekan yang tu je lah.
Cuba tekan.
Okay. Oh, dia share entire screen ke boleh pilih?
Boleh share entire screen tak? Ke boleh pilih
Entire screen, kejap kita try dulu. Sebab saya tak nak share entire screen. Boleh pilih window kan? So kalau window dia akan buka satu yang kita share je kan?
Betul.
Kalau kita buka a few documents, dia takkan nampak kita share another documents kan?
Betul. Cuba doktor
Saya try share window. Saya try PowerPoint dulu sebab selalu PowerPoint saya tak gerak. So saya selalu present PDF.
Oh, okay.
Sekarang nampak kan? Nampak.
Okay.
Lepas tu kejap saya gerakkan, nampak tak?
Dia macam tak moving lah.
Itulah dia. Kenapa? Sebab guna version
Ini daripada PowerPoint ke apa?
Ni daripada PowerPoint. Saya guna slideshow lah. Bukan.
Tapi sebelum ni banyak problem kalau guna Windows tak boleh. Kalau entire screen baru boleh.
Itulah pasal saya tak nak show entire screen. So kalau saya present guna PDF je boleh kan? Kejap dia dah stop sharing ke? Kejap kalau saya try ni kejap kalau saya share PDF macam ni, okey tak?
Dia pilih macam mana?
Ini PDF. So kalau saya share PDF, okey je kan?
As long as orang boleh nampak okey.
Nampak kan dia gerak kan? Okay. So saya share PDF je lah ya. Nampak full ke? Kena kecilkan sikit. Kecil sangat
tak berapa kurang sikit.
Kalau saya share macam ni je, boleh?
Kejap kita tanya chairperson. Chairperson boleh masuk. Dr. Anani boleh masuk. Doktor boleh share us to share audio and video.
Nurul cakap dengan saya ke?
Oh tak, saya cakap dengan Dr. Anani.
Assalamualaikum warahmatullahi. Boleh dengar tak?
Waalaikumsalam
Boleh.
warahmatullahi wabarakatuh.
Untuk Dr. Nur Azrina dah okey ke?
Cuba next slide boleh? Sebab ni memang tulisan besar. Cuba kita tengok tulisan yang kecil-kecil lain. Boleh tak Doktor next?
Yang ni nampak?
Yang ni clear.
So boleh je lah saya share in PDF.
Aku nak tengok. Mr. Adiola, can you please mute your... Mr. Adiola, can you hear
Sorry.
us?
Yeah, I
Can
can hear
please
you.
mute yours? Because you are making some...
I think it's okay now, right?
Yes, now it's okay.
Yang ni nampak
Yang ni nampak. Boleh next.
So saya ni dah conclusion dah. Kira ni tulisan paling kecil. So kalau boleh nampak saya share macam ni je lah.
Okay.
Sebab bila share in PowerPoint dia tak gerak.
Okay. Sebab yang ni paling kecil ya. Sebab saya nampak sekarang fabrication of ni title lah. Citosan film. Betul ke?
Tak, saya
Doktor
dah
sharing?
Saya dekat conclusion.
Bukan. Kita nampak dekat first page.
Oh ya?
Mm-mm.
Sebab dekat skrin saya nampak dia dah berubah-ubah. Kejap saya share lagi sekali. Stop sharing and share lagi sekali. Sekarang nampak?
Okay, sekarang kat conclusion tapi memang tak boleh dibaca lah tulisan tu, Doktor. Memang tak jelas, Doktor.
So saya kena besarkan lagi.
Kalau zoom inkan lagi.
Sekarang nampak?
Kalau besarkan sikit lagi boleh ke? Possible tak?
Besarkan lagi. Macam ni lah.
Okay, yang ni nampak.
And then present kena buka kamera ke?
Kita akan ada photo session. So waktu photo session tu kita minta untuk turn on camera.
So masa present tak buka pun tak apa
Boleh juga kot sebab takut kadang-kadang mengganggu internet connection kan untuk sesetengah orang.
Ya, betul. Okay, so saya present as PDF lah. Okay, thank you.
Okay, Miss Nurul, boleh proceed ke macam mana ya kita?
Semua partisipan dah ready ke?
Semua partisipan dah ready untuk dah share slide ke? Belum kan? Ke ada yang nak share slide dulu untuk tengok sama ada boleh dibaca ataupun tidak? Before we start, sekejap lagi kita nak start.
We still have another participant, right? Rabiatul Adawiyah, Madam Rabiatul. Okay. So I guess all of us are already here, right?
So nak check slideshow dulu ke? Ke tak perlu?
Saya ke?
Doktor dah untuk partisipan lain. Nak check ke Kita just proceed saja ya.
Prop 103 has not joined yet. He's one of the evaluator.
Again, Abu, may I?
Prop 103 has not joined yet.
Oh,
He's
okay.
the evaluator for the session.
Our evaluator is not yet. Okay, I'll remind them.
Okay. So before that, just a mic checking here. So Assalamualaikum and very good afternoon to all, ladies and gentlemen. So we are about to begin our session. Please stand by to all participants. So I would like to seek for your kind cooperation to avoid any virtual disturbance during this session. If you have any question, the conference resource personnel are ready to attend you. Thank you for your kind cooperation, and then we will start maybe 5 minutes from now. Thank you.
Hello, can anyone hear me?
Yes,
No,
Mr. Ahmad.
I'm testing my mic.
Oh,
Sorry.
okay.
Thank you.
Okay. Okay. Assalamualaikum, ladies and gentlemen. So now we are still waiting for Prof. Wan Jeffrey as an evaluator for today's session. While waiting for Professor Wan Jeffrey, here are some announcements that I would like to make for your kind attention. So for today's session, the oral presentations will be evaluated for the awards under 2 categories. Best session presenter that will receive the certificate for best presenter, and I will announce at the end of the session. And then best presenter award that offered prize money from 500 to 1,000 ringgit, trophy and award certificate. This will be announced during the closing ceremony. So I would like to seek for your kind cooperation to mute your mic if you are not presenting and to avoid any disturbance during this session. And then for those who intend to ask question to presenter, you can channel your question in the Q&A box, and then I will read it after presentation. All presenters are given 15 minutes for presentation and 5 minutes for Q&A session. And for invited speakers, you are given 25 minutes for presentation and 5 minutes for Q&A session. I will remind the presenter to end the presentation 2 minutes before the presentation session ends. Okay, and I will stop the presentation sessions when the session has exceeded the 5 minutes allowed. Before we start after this, I would appreciate if everybody can turn on the camera. But before that, let's wait for Prof. Wan Jeffrey and then we will continue with our session. Thank you for your kind cooperation.
Prof and Jeff, are you here? Prof?
Oh, okay. So I get to know from Dr. Alia that Prof. Wan Jeff already joined us. Thank you, Prof, for joining us today. So we are about to start our session. Assalamualaikum and a very good afternoon, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis 2021. Now we are in the session of Nanoelectronic, Photonic and Optic. My name is Hanani Suhaimi and I will be the session chair for today together with the session IT personnel, Ms. Nurul Azri Khalisah and also Mr. Abu Hashim. Okay. So as requested just now, if possible, we would be happy if you can turn on your camera for photo session. Okay, thank you. Thank you. So please smile, cheese. 1, 2, 3. Okay. One more. Smile. 1, 2, 3. Okay, thank you everybody for your cooperation. Without further delay,
Sorry,
let's...
the Prof just joined.
Yes?
One Jeffrey just joined.
Ah, okay.
You
So Mr.
can take another photo with him.
Oh, okay. Okay, let's take one more photo with Prof. Wan Jeffrey, maybe. Prof, can you turn on your camera so that we can have a photo session, please?
Okay.
Okay, never mind. Maybe there's some internet connection. So without further delay, let's proceed with our first presenter. The first presenter is Dr. Nur Azrina binti Yusof with the title Metal Oxide Biopolymer Film Accelerable Absorber for Q-switch Fibre Laser Generation at 1 micrometer wavelength region. Please welcome Dr. Nur Azrina binti Yusof.
Thank you, Ms. Hanani. Let me share my slide first. Can you see my slide?
Yes, doctor.
It's moving or not?
Yes, moving.
Okay. So I'm sorry because I have to present it in PDF because I have problem with my PowerPoint. So I will present it in PDF, okay? So hopefully you can read all the words. Okay, let's begin. So Assalamualaikum and good afternoon. I'm Nur Azrina Yusof from Photonics Research Center, UNIST Malaya. So today I'm going to share with you one of my research work entitled Metal Oxide Biopolymer Film as Heterobic Example for Q-switch fiber laser generation. So the basic idea of this project is we will manipulate the nonlinear optical properties of metal oxide, such as modulation depth and nonlinear absorption coefficient, to produce a pulse fiber laser at a specific wavelength. The nonlinear optical properties of material arise when there is an interaction of radiation with the metal or our material. So in which the polarization density will respond nonlinearly to the electric field of the light. So this will result in the variation of optical constant.
Sorry, Doctor,
Yes?
for disturbing.
Yes.
Because I cannot see the slide moving. So, or are you still in the front page?
Yes, still in the first page.
Oh, okay then. Oh, I
Okay.
thought that you already. Okay, sorry. Thank you.
Okay. This will result in the variation of optical constants such as absorption and index of refraction. So this phenomenon is usually accompanied by the generation of new optical frequencies. So in this work, I will use nickel oxide with chitosan as the media or heterobic absorber to help in inducing the pulse fiber laser at C-band wavelength region. There is in between 1530 nanometer and 1565 nanometer. So this is the outline for my today's presentation. I will start by giving a brief introduction on the development of fiber laser and its application, C-band wavelength region, mechanism of Q-switch fiber laser and heterobic absorber. Next, we will go to the experimental part where I will show you on how to fabricate the nickel oxide chitosan film and its characterization, followed by how to set up the fiber laser cavity and its characterization, and lastly, the conclusion. Okay. So the introduction about the development of fiber laser. The discovery of fiber laser has initiated decades ago, and it grows rapidly until today, following a period of dedicated work. The optical fiber laser was chosen to extemporize in scientific and industrial owing to its characteristic of compact structure, flexibility, reliable, and good beam quality. So fiber laser technology was started with development of telecommunication by integrating fiber amplifier of rare earth doped fiber, and it initiates the breakthrough of fiber laser in diverse application. So this is some of the rare earth element that's been used as the gain medium in the fiber laser. So fiber laser is a mature technology that has been an essential tool in facilitating wide range of scientific, industrial, and medical application. Such application of fiber laser to date until now are as follows. The first one is material processing. So people use laser as a versatile and flexible source for material processing. Fiber laser offer ultimate in solid state reliability and convenience. The advantages of high power fiber laser offer both conventional processing and processing with other laser types to prefer choice for cutting, drilling, welding, engraving, and many more. Next is LiDAR. It is an acronym for light detection and ranging. It is a remote sensing method that uses pulse laser to measure variable distances and generate precise three-dimensional data. The key component of quality LiDAR system is the laser source transmitting the beam. So this laser system must have short pulses, narrow line width, high peak power, and high repetition rate. Next is the medical surgery. So short pulse laser offer the surgeon the possibility of precision cutting tissue with virtually no thermal or mechanical damage to surrounding area. And lastly, the skin treatment. For skin treatment, it's aimed to destroy the target cell and not to harm surrounding tissue. So short pulses reduce the amount that the damaged cell hit, thereby reducing thermal injury that result in scarring. So this is some of the application for fiber laser. Okay, next the introduction about C-band wavelength region. The electromagnetic spectrum comprises the span of all electromagnetic radiation and consists of many sub-ranges, commonly referred to as portion such as visible light or ultraviolet radiation. So these various portions bear different names based on difference in behavior in the emission, transmission, and absorption of the corresponding waves, and also based on their different practical application. So basically, near all frequencies and wavelength of electromagnetic radiation can use for spectroscopy. But for fiber optic communication is mainly conducted in wavelength region where optical fiber have small transmission loss. So this low loss wavelength region ranges from 1260 nanometer to 1625 nanometer is divided into 5 wavelength bands referred to O, E, S, C, L, and U band. So today optical fibers show its lowest loss in the C band region or conventional band, that is in between 1530 nanometer to 1565 nanometer. This is commonly used in many metro, long haul, ultra long haul, and submarine optical transmission system. Besides that, C-band also has been used in many satellite communication and some Wi-Fi devices. It also has been used in medical and industrial heating application and other applications such as cordless phone, baby monitors, and keyless entry system for vehicles. Okay, Q-switch laser, the mechanism. So pulse fiber laser can be generated using passive Q-switching technique. This passive Q-switching involves the modulation loss obtained by incorporating a nonlinear optical material with intensity-dependent transmission properties, or we call it as a saturable absorber. So this slide shows the schematic setup of passively Q-switch laser, which consists of a high reflective mirror, laser active medium, output coupler, and saturable absorber is placed within the laser resonator. So this process involves the loss and gain pattern. Here, loss and gain pattern of the laser resonator for the generation of output pulses. So when we place SA or saturable absorber inside the cavity is in high loss due to absorption of low intensity light. So here, first, it have high loss due to low intensity light. So there is no lasing occur here at point 1. However, the laser inversion is established through pumping process after some time. So the gain will be larger than total loss here. So lasing begin at lower power. So the excited state of saturable absorber populated and saturable absorber will saturate. So at this stage 4, so based on this figure, when the gain is equal to loss, here the gain is equal to loss, so we can see the optical power rise. So we can see the peak power here at stage 4. So after some time, the extraction of energy from gain medium cause gain to saturate. So it will start to saturate after stage 4. And making the lasing to stop and end the pulse. So here, there is no more lasing at stage 5 here. So this is how the pulse fiber laser is generating using Q switching technique with the help of SE. Okay. So the technique of using saturable absorber is often preferred as they enable wide space of pulse parameter to access without employing costly and complex electricity driven modulator. So when using this, there are a lot of technique to generate pulse laser, and one of it is saturable absorber. And we choose saturable absorber because we don't have to use any expensive and complex modulator. So the real saturable absorber exhibit an intrinsic nonlinear decrease in absorption with increasing light intensity, such as dyes or colored glass, CSAM, or we call it semiconductor saturable absorber mirror, and other type of nanomaterials. So in this work, nickel oxide nanoparticle crafted with chitosan is used as saturable absorber to generate a tunable Q-switch fiber laser in C-band region by using erbium dope fiber as the gain medium. So why we choose nickel oxide? So nickel oxide was chosen as the saturable absorber material due to its series of advantages in the domain of optical properties such as broad absorption bandwidth, high damage threshold, and low saturation intensity. These excellent optical properties meet the essential criteria of a good passive saturable absorber, which in turn help in boosting the overall performance of fiber laser. So other than that, it also offers prospect of large production with low cost and easy preparation process. And then why we use chitosan? So in this work, chitosan is introduced as the polymer host for fabricating the thin film for saturable absorber, as it has excellent film forming capacity as well as high biocompatibility, good bioactivity, and high biodegradability, and also non-toxicity. Besides that, chitosan also has been widely used in fiber optic sensor for multiple purpose, and we were keen to explore the possibility of chitosan as one of the dry material for saturable absorber, thus enhancing the quality of saturable absorber. So besides chitosan, we can also use other type of polymer, but in this work, we try to play around with the biopolymer and see how it affects the performance of our laser. So now we go to experimental part, the fabrication of nickel oxide chitosan film. So as I mentioned before, nickel oxide chitosan film is used in this work as saturable absorber. So initially, nickel oxide nanoparticle is synthesized using sonochemical method and followed by solution casting method to form the film here. So there are two steps here. First, we need to synthesize nickel oxide nanoparticle first, and then mix with catalysis and to form the film. And this film will be used as a rubber absorber to induce the generation of fiber laser in our work. So in this work, we use sonochemical method. So
Okay, Doctor.
yeah.
So actually the time session for you is about to end. So it is advised for you to conclude your presentation before the session ends. Thank you.
So after we get the film, so we will characterize it. This is a basic characterization, XRD, UVs, and tuck plot. So from XRD, you can see all these sharp peaks belong to nickel oxide, and it has a sharp peak. That means it's has high crystallinity. And based on this UVs result, we plot the tuck plot and measure the band gap of this film, and we get around 3.51 EV. So this is the FSM result. You can see there it have a spherical nanoparticle shape with a diameter less than 25 nanometer. And this is the nonlinear absorption spectrum for nickel oxide catalysis film. And from this graph, we measure the modulation depth, non-saturable loss, and saturation intensity of this film. So this is the cavity that we use to generate the pulse fiber laser, and our film will be insert in this part, at this part. Okay, after we insert our film, and then we can generate the laser. And this is the instrument that we use to characterize our pulse laser. We use oscilloscope, RFSA, and optical power meter. So this is the typical laser characteristic we obtain in this work. So from this work, at the pump power of 171.3 milliwatt, we can get pulse laser at a central wavelength of 1562 nanometer, which is in the C-band region, with a 3D bandwidth of 1.33 nanometer and pulse width of 2.9 microsecond, with repetition rate of 29.3 kilohertz and SNR, or signal to noise ratio, of 43.26 dB. So this is the result when we vary the pump power. You can see there is an increasing trend. So this is the typical characteristic of pulse laser when operating in Q switching technique. So other than generate the pulse laser, we also study the stability and tunability of our generated laser. And it shows that our pulse laser have high stability, and it can also be tuned from 1522 nanometer to 1580 nanometer. That is covering the C and L band as well as portion of S band. So as a conclusion, passive Q-switch fiber laser based on erbium doped fiber as the gain media and using nickel oxide catalysis film as SA was demonstrated. So the advantages of catalysis film, which includes its biocompatibility, non-toxicity, and high thermal resistance, make it a highly attractive candidate material for rubber absorber fabrication. The proposed rubber absorber will have many practical photonic applications, particularly for optical signal processing and optical fiber communication system. So that's all from me. So if you have any further question, you can always contact me at this email, and phone number. Okay, thank you.
Okay, thank you so much, Dr. Nur Aziana, for your very great sharing. So now we have one question for you from Mr. Adiola Akinpelu. The question is, what is the novelty of this work? Please.
Okay, for this work, actually, as I mentioned before, we try to use other than conventional polymer like PVA and PEO to form a film. We try to mix our nickel oxide with biopolymer and see how it affects our laser performance. So I think it's on the film fabrication itself.
Okay. I hope it's answering your question, Mr. Adiola. So now let's move along to the next presenter. Now please welcome Mr. Muhammad Aiman Saufi bin Ahmad Fahri with the presentation entitled Non-Linear Optical Properties of Molybdenum Disulfide. Please welcome.
Sorry. Okay, so first of all, can you hear me?
Yes, we can hear you.
Okay. So good evening to everyone in this room. So my name is Muhammad Aiman Saufi bin Ahmad Fahri. I'm a master student in Department of Physics and Photonics Research Center UM. Okay, so for today, first of all, I would like to apologize to the committee member because I have I have I have changed my title into nonlinear optical properties of zinc oxide variants. This is due to the last minute decision between me and my supervisor. So this work is a collaborative research of Associate Professor Dr. Rosalina from PRCUM and Dr. Vivi Fauzia from University of Indonesia. Okay, so for this experiment, so I will explain to about the introduction, methodology, results, and also the conclusion. Okay, so first for the introduction. So the objective of this experiment are first is to prepare the zinc oxide and zinc oxide with nanoparticles using appropriate method and on a substrate for Z-scan measurement. Second one is to evaluate the optical nonlinearity parameters of the zinc oxide variants from Z-scan measurement. Okay, so first for the introduction of the theoretical aspect. So nonlinear optics is a process where polarization of a material is dependent on the strength of an applied optical field. So we can say that in the case of linear optics, polarization is equal to the permittivity of free space times with the linear susceptibility of a material times with the strength of optical field. So we can say that the the polarization is directly proportional to the applied optical field for linear optics. In the case of nonlinear optics, we extend to the power series of for the expression. So the polarization is equal to the permittivity of free space and the susceptibility and the strength of optical field is extended using power series method, where we can see that they have first order, second order, third order, and so on. So we can say that polarization, total polarization of a material can be described in the first order polarization, second order, third order, and so on. So from the second order of polarization, we can obtain a second order nonlinear optics mathematical description, which is as shown as in the screen. So there exists the 2 omega, where the 2 omega from the first term on the right hand side, there exists the 2 omega, which is the second harmonic generation, and the second term is the sum frequency generation of second order nonlinear optics. And then for third order nonlinear optics, we have 2 terms, which we can see that the 3 omega is the third harmonic generation, and the second term shows the self-focusing effect. So we can say that second and third harmonic generation, SSG and THG, appear based on this equation. So in a figure, we can say that for second harmonic, two frequency will incident on the material and generated at two times the frequency, and so does the third harmonic, which is three similar frequency that generated 3 omega, three times the frequency. So next for Z-scan, so the measurement, so in theoretical, a Z-scan is where we use a high intensity laser incident to a focusing lens, which appear here, and then producing a focusing point. So the focusing point is the Z naught, area, which is Z equals to 0. Z equals to Z naught. So at the focusing point, there exists the beam width radius, which is the W naught, which we can relate to the Z naught equals to pi omega naught squared over the wavelength of the laser, which is the parameter here is called the Rayleigh length. So for Z-scan, there is 2 type of measurement: open aperture and closed aperture. So for open aperture, we will measure the nonlinear absorption of a material, and for closed aperture, we will measure the nonlinear refractive index. As you can see, for both of these transmission description, both depends on the Rayleigh length. So for a material, any material have a third order nonlinear susceptibility. So the third order, the chi3 is a non-vanishing parameter for any material. So that's why we calculate the chi3. Okay, so the chi3 can be differentiated into 2, real and imaginary part, which is the real part of chi3 is dependent on the gamma, which is the nonlinear refractive index, and imaginary chi3 is dependent on the nonlinear absorption. So we can get the value if we take the Pythagorean expression. Okay, next for the methodology. So for sample preparation, zinc oxide was prepared by 2-step process: seeding process via ultrasonic spray pyrolysis and growth process via hydrothermal methods. For AuAg nanoparticles, for this experiment we use gold and silver. So AuAg nanoparticles, the method used was chemical reduction. So AuAg precursor solution contain 5 millimole of auric acid and argentum nitride with different mole ratios of 1 to 0, 3 to 1, and 1 to 1. So 1 to 0 is, for example, gold with no silver. So 3 to 1 is 3 parts gold and 1 part silver. 1 to 1 is 1 part gold, 1 part silver. Okay, so the zinc oxide nanorods were then immersed in the precursor AG solution and heated for nanoparticle structure. So next for the setup, before we go to the setup, the sample preparation was done by our collaborator from University Indonesia. So for Z-scan setup, we use this similar setup. So the first one is the laser pump, the laser as a pump source. For the laser, we use femtosecond laser with pulse rate of 100 femtosecond and repetition rate of 82 megahertz with wavelength of 720 nanometer. So for the length, we use biconvex with the focal length of 25 millimeter, and we obtain the beam width at the sample Z path. And then we have a detector and the aperture. The aperture is for the closed aperture setup, which is for open is open. The S parameter is S equal to 1 for open, and closed is between 0 to 1. And then we analyze the data. So next for the results and discussion. So the sample thickness obtained by surface profiler. So we can get the linear absorption, which is shown in alpha in this row, in this column. So next for the open aperture, we obtain a graph of as shown. So the zinc oxide nanorod only shows negative beta, which is a saturable absorption property. And for the associate with the nanoparticle, the zinc oxide with the nanoparticles shows positive B, which is the reverse saturable absorption. So we can say that this process regarding the nanoparticle is said to be the two-photon absorption process. So for closed aperture, we obtain like as shown in the figure. So the zinc oxide nanorod shows positive gamma, which is the self-focusing effect, which is a peak to valley graph. For the remaining nanoparticles, they shows negative gamma, which is a self-defocusing effect. So this can be said that the sample experienced phase change of refractive index non-linearly. So we tabulated the nonlinearity optical parameters. So for each material, zinc nanorods, gold nanoparticle, gold silver, and gold 3, silver 1 nanoparticle. So we obtain the chi, the third order nonlinear susceptibility as shown in the table. So the gold exhibits higher susceptibility compared to others, but small difference with the one to one AuAg. So for conclusion, as a conclusion, so based on the objective, zinc oxide and zinc oxide with nanoparticles successfully prepared using seeding process, growth process, and chemical reduction on a substrate for Z-scan measurement. And the second one, the optical nonlinearity parameters of zinc oxide variance from Z-scan measurement is evaluated and resulted that zinc oxide with gold have the highest third order nonlinear susceptibility with small difference value from zinc oxide with 1:1 gold silver. So that's all from me. Thank you for your attention.
Okay, thank you so much, Mr. Muhammad Aiman, for your presentation. So for all participants, if you have any question, you are most welcome to write it on in the chat box so that we can ask our presenter. Okay, now we have one question again from Mr. Adiola Akimpelu. The question sounds, does it have real life application? Please, Mr. Aiman.
So at this point, we don't. At this point, we didn't explore that part of the research for real life application. But right now we're working on how to how to relate any material with a nonlinear effect. For example, if a material incident towards a high intense laser. So for that question, I cannot give the exact answer. That's all I can say.
Okay, thank you for that. And also, Mr. Adiola would like to know what is the novelty of this research?
So for the novelty for this research is the merging of nanoparticle and semiconductor nanoparticle and semiconductor material, and due to that it can use as a photocatalyst that can enhance the drawbacks of zinc oxide due to the rapid recombination of electron hole pairs in the zinc oxide. So merging with the nanoparticle can enhance can overcome the drawbacks of zinc oxide material only. That's all.
Okay, thank you. And I have one question to ask. As we all know that zinc oxide is actually extensively used in many studies. And then can you comment on what is the future of this study? Can you please comment on that?
I can comment, but I didn't, but I don't have the exact answer. But I can try. Okay, so zinc oxide is widely used by many researchers, and but for and also by merging with the nanoparticle. But I did some searching and I found out that not many researchers doing on the nonlinear aspects of studies for specifically for zinc oxide merging with nanoparticles. But so that's what we would like to try for this research.
Okay, thank you, Mr. Muhammad Aiman. So now let's move on to our next presenter. Now let's welcome Madam Rabiatul Adawiyah binti Muhammad Akhir with the title A Review on Zinc Oxide Nanorods for Optoelectronic Applications a perspective on biosynthesis approach. So, Madam Rabiatul Adawiyah, please welcome. Madam Rabiatul Adawiyah, please unmute your speaker. Thank you. Sorry for disturbing Madam Rabiatul Adawiyah. It's just that we still cannot hear you. And your speaker is still in mute condition. No, we still cannot hear you.
Select a microphone. The microphone. Okay. Apply now. Apply. Oh, no, it's haven't changed. Not yet.
We
Please
cannot hear
select
you.
microphone.
Maybe IT personnel can take in charge of this.
There is problem in her settings. Go again and select microphone. You have select communication. That is why microphone. Yes. Yes. Apply.
All right. Okay. All right. Thank you. I'm sorry for the inconvenience. All right. So let's move to the next slide. All right. Okay, so my title today is a review on zinc oxide nanorods for UV sensor application with some of perspective on biosynthesis approach. And so let me have a very quick introduction on what motivates us on to study and to review on zinc oxide. As mentioned by previous speaker just now, zinc oxide have been tremendously used in various applications. So, and it have been reported that around 10 power of 5 tons per year have been produced. So meaning to say that zinc oxide have relatively low toxicity. So that's why it has been used in various applications. So moving towards biosynthesis overview. So from 2000 to 2020, zinc oxide synthesis have been started with mechanochemical process and then followed by chemical vapor deposition. However, they using extreme synthesis condition. And so that's why the researcher moved to the solution immersion, which is quite environmental friendly. And recently on 2018, Vishnu Kumar et al. Have reported the biosynthesis by using plant-based synthesis to produce a comparatively high crystalline zinc oxide with low energy as well as compared to the solution immersion and with environmental friendly effect. And in terms of zinc oxide nanorods, the first starting phase that might be other researcher can start is to focus on the zinc oxide seed layer by using biosynthesis technique. This is what I have been read throughout the recent progress. So they suggest to try use the biosynthesis approach on the preparation of zinc oxide seed layer to maintain the environmental effect. So here is some of the biosynthesis of zinc oxide nanostructures. So this table summarize the most of targeted application is towards
biomedicine application and a very few in optoelectronics application if using biosynthesis process. And the size of zinc oxide particles also very challenging to obtain below than 100 nanometer. And this is the conventional biosynthesis method look like from plant extract and mixed with the precursor zinc nitrate or zinc acetate, and then followed by drying process, they obtain the zinc oxide nano powder. And this is what I mean by conventional or traditional biosynthesis method. All right. Okay. So in terms of mechanism behind how the biosynthesis method can produce zinc oxide nanostructure is that one of that is they have been doing the Flavonoid Test, the first test to screen whether there is or not a phytochemical compound present in the that particular plant. For example, in the Pandanus mellifolious leaf, there have been study reported that there is a flavonoid content consists in this plant. So this flavonoid content that responsible in reducing the metal zinc into the zero valence state, and then through calcination, the oxide may be added to the metal. And then from figure 5 here, it is interesting to see at the C effect of reaction time and also effect of extract volume. So from here, we can understand that the optimization process does play a role into producing rod shape of the zinc oxide. And then moving to zinc oxide nanorods via solution immersion method. So this is the typical solution immersion process that have been used by previous researcher. So usually in environmental technique, the previous researcher claimed that by using zinc nitrate and HMTA, it is more like environmentally friendly technique due to its water-based nature, and then followed by spin coating technique to produce zinc oxide seed layer, and then to have this diagram, and then after that followed by solution immersion process as this diagram, and finally the zinc oxide nanorods have been produced on top of biosynthesized zinc oxide seed layer here. And this is some of the findings from previous studies. So as we can see here, on last year, Chow et al. Have produced quite vertical aligned nanorods by hydrothermal method. But the hydrothermal method here actually is referring to the same solution immersion method. It's just that they use the hydrothermal term because of the sample is being, the glass substrate is being put into the vessel and then kept sealed and then undergo the heating process at several temperature and several time. So the researcher doesn't use any pressure or any autoclave system. So it's still referring to the conventional solution immersion process. And then here, figure 8, here is the surface morphology and XRD data of zinc oxide nanorod grown on TiO2 seed layer. So it is quite interesting. We can play around with the any types of seed layer. I mean, what are the effect of using any using other seed layer towards construction of the zinc oxide nanorods. As we can see here, less vertical aligned nanorods have been produced when it has been deposited onto TiO2 seed layer. So this is quite understand because due to the different materials between TiO2 and the zinc oxide itself, so it's produced the mismatch, the lattice mismatch between the two phases. And then we move to the zinc oxide produced from biosynthesis. So what are the research issues that actually we are going to tackle here now is because of high toxicity waste, as in this diagram from Ulhaq 2017. So they have outlined this from the zinc oxide synthesis, from the throughout the whole synthesis, and what happened to the our environment, for water, air, and for the soil. Because throughout the whole synthesis, there might be application of relatively high toxic materials, such as a very high concentration of sodium hydroxide that have been used in previous study, for almost high that to 10 molar of sodium hydroxide. So that is very quite challenging to overcome. And then from these issues, Erkan 2018 et al. Have developed this method, this green synthesis method or biosynthesis method, by using menthol leaf as a stabilizer. And they have able to produce enhanced 002 peak in their SRD data. However, still producing nanorods that random and free distribution of rod structure. So that's is leave room for improvement for us. Another comparison with previous research findings is that we can see a various random rod structure have been produced by using plant-mediated synthesis. So from 2015 until current 2019. So it's still challenging to produce a vertically aligned rod structure. Nevertheless, I was very interested with previous talk from Prof. Amanda. She mentioned that any bad results, no such thing as any bad results. I mean, we should appreciate any results from our experiment. So yeah, that is the motivation for us, especially for postgraduate students. Yeah, since this pandemic, we cannot go to the lab. So this is what at least that we can do lah, to do the review, to study the recent progress in our particular research topic. Okay, and then so here is the SRD data produced as comparison with two researcher here. So here you can see the 002 peak is still yet need a major improvement in near future. So in conclusion, to obtain vertically aligned nanorod of zinc oxide nanorod synthesis using modified biosynthesis is still remain a challenge. And then as a brief on the UV sensor, so this is what the latest study that I can find, that using environment zinc oxide nanorod base used for the UV sensor, and this have been reported by Asip et al. 2020 last year, which they have reported that almost 99.8% are more sensitive when they are using their material zinc oxide nanorods on TiO2 seed layer as compared to the pure zinc oxide nanorods. And then similar outcomes were also summarized by Sutina et al., where the nanocomposite devices had exhibited high responsibility, photocurrent, and good reliability as compared to pure zinc oxide nanorod devices. So we can say that we can improve the zinc oxide nanorods, the pure zinc oxide nanorods, so that it can have similar or at least same with the composite one. And as conclusion, we have outlined 5 conclusions. So the goal of this review is to bridge the gap between traditional biosynthesis and a few plant-assisted solution immersion methods. And then we also understand that the variety of morphologies in the solution immersion have further broadened the UV sensing applications. And then the novelty offers some insights to the progress of plant-mediated synthesis of zinc oxide, especially in nanorod shape. And then nevertheless, we also find some significant challenges here. For the first one is to meet the balance between achieving environmentally zinc oxide nanorods and its efficacy towards the UV sensor application, because we don't want it's just green but not really efficient. And then number two, to determine the exact parameter optimization to increase the properties of zinc oxide nanorods, and lastly to determine the exact mechanism between the role of plant in the biosynthesis of zinc oxide nanorods. So that's all from me, and some of the acknowledgement. I would like to say thank you to my supervisors and to all my colleagues. So that's all. Thank you.
Okay, thank you, Madam Rabi'atul Adawiyah. It's such an interesting topic on zinc oxide nanorod. Okay, I have one question for you. We understand that zinc oxide exists in many forms like nanorod, nanotube, as well as nanoparticles. From your own opinion, not only limited on your application, which structure actually is the best from your own study, from your opinion?
Okay, from my opinion, the structure that give the best, the best structure is very it's depending on what kind of application that you are targeting. For instance, in antibacterial activity, the structure such as nanoparticles or nanoflowers in 3D structure is more preferred. But for UV sensor, based on my understanding so far, the one dimension nanostructure, the nanorod structure, tends to have a best nanostructure compared to the nanoparticle due to its vertical structure that allow the movement of the electron to pass easily from one point to another point. Yeah, it's based on the application from my understanding.
Okay. So the structure much more depending on the application itself.
Yeah. So all structure have their specific application.
Okay, thank you for your explanation,
Thank
Madam
you.
Rabi'atul Adawiyah. So now we are moving on to the next session with our invited speaker, IR Dr. Hanim Hussein. She will be talking on investigation on sensitivity application effect of double gate field effect transistor based pH sensor. Please welcome.
Okay, can you hear my voice?
Yes, doctor, we can hear you.
Okay, Assalamualaikum and good day to everyone. I'm Hanim Hussein, lecturer from College of Engineering, University Technology Mara, and currently attached with Center of Printable Electronics, University of Malaya. I'm going to present the work on the investigation on sensitivity amplification factors of double gate field effect transistor based pH sensor. The co-author of this paper are Professor Nur Hayati Soin, Dr. Yasmin Abdul Wahab, and also Dr. Maizan Muhammad. Okay, so the outline for my presentation today, I will give some introduction on the FET effect pH sensor, and then basic operation principle of FET devices as pH sensor, and methodology of this work, result and discussion, and lastly on the conclusion. Okay, the ion sensitive field effect transistor is FET sensor first introduced by Pete Bulbert in 1970 is based on the potentiometric techniques that has been extensively investigated as a transducer due to its potential for label-free detection, fast response, miniaturization, easy integration, parallel sensing, low cost and compatibility with state-of-the-art CMOS manufacturing technologies. Okay. In principle, the pH sensitivity of a single gate FET based sensor can achieve maximum pH sensitivity defined by the Nash response of 55 millivolt per pH. Okay, pH FET devices for the pH sensing have been utilized in a wide range of applications such as in healthcare, environmental monitoring, and also in the food safety. As can be seen in the figure here, in the middle is more advanced technology of FET, which is it is based on the organic material to design and develop the FET based sensor. Okay, we call it as OFET. Okay, however, the electrolyte screening and semiconductor capacitance lowered the theoretical response limit. Okay, this limitation can be improved by employing different configuration of FET. Okay, we have double gated field effect transistors, DGFET, and also extended gate field effect transistor, EGFET. Other than different configuration, researchers also focus on using different type of channel materials, different type of dielectric material, as well as optimizing the biasing conditions. The figures here shows three different structures. A is the normal ISFET, the single ISFET, and B is the double gate FET, and C is the extended gate FET. The normal ISFET here is similar to FET device, okay, but you can see that the gate electrode is consists of the reference electrode connected to the electrolyte here. Okay, the type of electrolyte, the biasing configuration will determine the amount of current that flow between the source and drain. Okay, for the B is the double gated FET. Okay, we have two gates. For the top, which is the reference electrode connected to the electrolyte, and the bottom gate, and also we have two oxide layers. Okay, this technology can increase the sensitivity beyond the Nash limits. Okay, dual gate based biosensor enable sensitive detection with high intensity signal by their distinctive structure based on a combination of the solid, okay, the bottom gate here, and the liquid gates. Okay, so basically this work will be focusing on this kind of structure. The third one here is the extended gate FET. Okay, it consists of the transducer unit and also the detector unit. Okay, the transducer is basically the FET system, okay, where the top gate here is connected to the detector unit, which the detector consists of the reference electrode and also the electrolyte. Okay, and next I will explain on the basic operation principle of field effect devices as pH sensor. Okay, it is based on the potentiometric techniques. This technique allows the detection of hydrogen ions, H plus or H minus, that can measure changes in the dielectric electrolyte interface surface potential. Okay, based on the pH value of the electrolyte, protonation or deprotonation of the OH groups on the gate insulator led to the change in the dielectric surface charge. The protonation of the solution is because lower pH value will generate positive surface charges, while higher pH value will lead to the opposite. Okay, this is the potentiometric figure which we have the current flow here from the source and drain depending on the protonation or deprotonation process. This one is another example of the FET based sensor, okay, which the G and R graphene or nanorod is used as the active material, okay, between the electrolyte, and we have the pH sensor is controlled by the drain and also the gate voltage here. Okay. And for this work is based on the simulation work. So the formula or the model that used is basically the combination of the Guy-Chapman-Stern GCS model and side binding SV theory, okay, which this model can provide the relationship between the pH of the solution and the surface potential, which can be seen in this relationship here. The sensitivity over the pH equals 2.303 alpha kT over Q. Okay, where the phi 0 is the surface potential at the oxide electrolyte interface. Okay, alpha is a dimensionless sensitivity parameter. K is the Boltzmann constant, and T is the absolute temperature, and Q is the elementary charge. A change of the surface potential result in change of threshold voltage. Thus, the pH is measured by monitoring the shift of the threshold voltage. Okay, in this work, we use the Biosensor lab simulator, okay, to explore the effects of device geometry and bias condition on the pH sensitivity. Okay, the figure here shows the double gate FET biosensor structure used in this work. Okay, the planar type dual gate FET composed of the two gates. Okay, one is the top gate, the fluid gate here, which is the position, which is reference electron immersed in the solution. Okay, in this electrolyte here. And then the other one is back gate, the burette gate, which is positioned underneath the burette oxide of the SOI, is silicon on insulator. The driving voltage, which determines the FET characteristics, is set through the reference electrode, and the surface potential produced by the pH is then amplified through the back gate. Okay, although the pH sensitivity is limited by the properties of the gate dielectric, the surface potential produced on the gate dielectric is translated into VT and amplified into a larger signal by means of the dual gate structure. Okay, as you can see in the figure here, the model consists of nanoscale FET introduced to an electrolyte solution containing target biomolecules. As the biomolecule carries significant charges, this FET-based sensor can be used to detect them. Okay, it can be used to sense charged biomolecule like the pH of the electrolyte based on the protonation or the deprotonation reactions. Okay. The surface binding model was used to account for the protonation or deprotonation of OH groups, and the chemical reaction occurred on the silicon oxide surface, okay, as can be seen here, the relationship. Okay, the HS plus represent the proton density near the surface region. Ka and Kb are the equilibrium constants. The surface group protonation or deprotonation affinity defined by as pKa and pKb, okay, which pKa is negative log 10 Ka and pKb is negative log 10 Kb. Okay. The total density of surface group is given by the Ns, SiOH plus SiH2 plus SiO minus. Okay, so this table is for the side binding model parameters for each of the oxide, dielectric oxide used in this work. Okay. And based on this work, it is using this drain current formulation, which is based on drift division formalism. Okay, because of this DGFET sensors are long channel devices, okay, which you can see the length are varied here based on 0.25, 1 and 10 micrometer. And the drain voltage applied is 0.1, 0.5 volt, okay, because of smaller VDS is required for the biosensing application, okay. And then as we can see that the geometry of DGFET, okay, based on the relationship here, the geometry W over L, the insulator thickness Ti, play an important role in electrical properties of the device, okay, which represent by this drain current. And this epsilon I, Ti, the dielectric constant and dielectric thickness. WL is the width and length of the transistor channel. The mu here is the mobility of the semiconducting channel. And the Vt here is the threshold voltage. Okay, the channel length and width, okay, channel length and width here, sensor width, sensor length here varied based on the long channel device, okay. The variation of top and back oxide thickness, okay, this is the top oxide, back oxide thickness are varied based on this 2 nanometer, 4 nanometer for top oxide and back oxide 50, 100 and 150 nanometer. And then in this simulation, the range of pH level used is from 3 to 9. And then based on this simulator, the underlying model formalism here is divided, okay, into 4 regions here. Okay, the region 1 is the front gate, fluid gate electrolyte interface. Region 2 here is the electrolyte. Region 3 here is the top oxide electrolyte. Okay, top oxide electrolyte. And then region 4 is the silicon oxide silicon FET system. Okay, and now is the result of this work. Okay, this figure here, figure 1, figure A and figure B is the transfer characteristics of double gate FET as a pH sensor. Okay, as we can see that as the pH value decreases from 9 to 3, the current increases, which indicates an increase in the conductance of DGFET, okay, basically for both front and back gate operation. Okay, figure A is a front gate, figure B is the back gate, IDVBG, IDVFG. Okay, both shows that as the pH decrease, current increase, okay, higher pH values decrease the drain current. So as for the explanation, for a solution that has a lower pH value, okay, more concentration of H plus ions were available in the buffer solution, which increased the positive charge density on the pH sensing layer, hence attracting the electrons in the silicon channel, subsequently increase the drain current. Okay, corresponding pH sensitivity was measured in terms of threshold voltage shift, where the backgate operation can amplify the sensitivity beyond the nurse limit. Okay, as we can see from this figure here, this is the resultant subsequent VTH shift for this axis based on the front gate and for this axis based on the back gate operation. Okay, for the front gate operation, we obtain the sensitivity is 21.4 millivolt per pH, but for BBG, for the back gate, it is above the National limit, which is the 161.5 millivolt per pH. Okay, basically the BG amplified factor by 8, okay, in this case. The supernation characteristics demonstrated by the DGFET was due to the asymmetry factor of front and back oxide capacitances. Okay, assuming capacitive coupling effect. Okay, the pH responsivity with capacitive coupling between the front or back gates and channel can be explained based on the effect of electrical potential being induced by the pH solution where the front gate side is capacitively coupled to the back gate through the channel. Okay, this is the basic underlying concept of DGFET in amplification sensitivity effect. Okay, the next one is the amplification factor based on different width and length ratio. Okay, and also effects of different top and bottom oxide thickness on the sensor performance. Okay, figure A and B here shows the transfer characteristic of DGFET simulated for the front and back gate operation. Okay, with different lengths for pH3 and pH9 respectively. pH3 in figure A and pH9 in figure B. The magnitude of the drain current is inversely proportional to the length of DGFET channel. Okay, smaller length will contribute to a higher current, okay, as shown in both figures. Okay, further investigation on the responsivity with respect to different width and length W/L ratio, okay, as can be seen in the table. Okay, the table shows the sensitivity of front and back gate operation and subsequent amplification percentage, okay, and amplification factor by back gate operation. Okay, from the table, it shows that sensitivity of DGFET sensor were not width and length dependent for both front and back gate operation. However, the amplification percentage and amplification factor were similar if W/L gives similar ratio regardless of the value of W and L. Okay, as for example here, we have W1, the length 1. So the ratio is 1 here. W is 10, length is 10. Okay, the ratio and 1, they have similar amplification factor. Okay, if there's W.1, the L1, okay, and W1, L10, okay, we have the ratio 0.1, we obtain the amplification, the same amplification factor 5. Okay, all range of the W/L DGFET simulated in this work gave sensitivity below Nash limit for front, this one. Okay, all here is below Nash limit, and for the back gate here above the Nash limit. Okay, this slide also shows all the back gate operation had sensitivity beyond the Nash limit. Okay, however, we can see as the bottom oxide thickness increase, okay, figure A here is figure A and figure B, both we fix the oxide to 2 nanometer and we vary the bottom oxide. Okay, for F, this figure A is the front operation, B is for back gate operation. For the back gate operation, we can see that as we increase the thickness of the bottom oxide, the responsivity, the sensitivity also increase. Okay, similar to we use top oxide thickness 4 nanometer, as we increase the bottom oxide thickness, the responsivity also increase, but not for the front gate operation. Okay, as we increase the bottom oxide, okay, the sensitivity not increase as well. Okay. Okay. The next slide here is we use different oxide dielectric, okay, to check on the sensitivity of the pH sensor. Okay. The dielectric used are the SiO2, the Al2O3, and Ta2O5. Okay. We can see from these 3 different dielectrics, SiO2 has the lowest responsivity. Okay, the VBG 178.5 millivolt. For the Al2O3, the VBG back gate operation produced to 10 millivolt. Ta2O5 produced 207 millivolt per pH. Okay. We can see that pH responsibility better for Al2O3 as compared to SiO2 here is because of due to the higher buffer capacity of the Al2O3 surface. Okay, high K dielectric such as the Al2O3, Ta2O5 was shown to be better than SiO2, and gate dielectric can be employed, and thicker gate dielectric can be employed without losing sensitivity to the charge, hence reduces the leakage current, which significantly become robust in fluid. And then Al2O3 offers sensitivity enhancement based on the increased dielectric constant that increase the capacitance, hence the sensitivity. Okay, and then as for conclusion, high pH sensitivity far above the Nelson limit was demonstrated through backgate operation of DGFET. The amplification was exhibited due to capacitive coupling effects contributed by the asymmetric thickness of front back oxide. Thicker back oxide thickness contribute to high sensitivity, while similar width over length ratio exhibited the same responsibility level. Okay, the use of high K dielectric such as the Al2O3 and Ta2O5 can further increase the sensitivity response. And then the DGFET sensor is one of the promising level free sensors to be used for various biological events, which can be further optimized through the geometrical configuration and the type of the dielectric use. Okay, with that, I end my presentation with thank you.
Okay. To me, I have one question. We see that the oxide thickness is in micrometer, and you mentioned that the application has limitation at certain thickness, right?
Yes.
Do you have any comments if the thickness in nanometer, does it mean that it is totally lost, or maybe it has something good at that different range? Thank you.
Okay, basically if we look at the oxide thickness, it is actually better if we have the very thin oxide thickness, but then we have other problem that we call it as leakage current, which if this leakage current very high, it actually can lead to the problem, or can has a degradation effect on the transistor performance itself.
I see. So it's already been stated that has a certain limit, so that you are going just play around in that certain limit.
Yes.
I see. Okay, thank you, Dr. Hanim, for your sharing. So now let's move on to our next invited speaker, Associate Professor Dr. Ong Moon Hong, with the title Metal Oxide Nanostructures Based Gas Sensor. If you are ready, Doctor, please welcome.
Thank you, Hanani. Can you all see my slide?
Yes, Doctor, I can see you.
Okay, good. Okay, good afternoon, everyone. It's always been very challenging to be the last speaker of a very long day conference. Anyways, I'm very grateful and very thankful to the organizers for your kind invitations. And in my sharing today's, I will deliver some of our latest works depending on these metal oxide nanostructures for the gas sensors applications. There's some backgrounds about the work. Ammonia has been commonly produced and widely used in various sectors in our daily life. It's a very important chemicals compounds, and it's also act like a fuse for hydrogen gas productions, which is a very promising sources of energies in our coming futures. So talking about the good side about this ammonia gas, and we also have the other sides, which is the dangers of this type of gases. So if normal human beings inhales more than 500 ppms, it will cause irritations to the nasal systems. And if you expose more than 1000 ppms, it can also will cause even much more severe health problems, which is the pulmonary edemas. This involves the accumulation of fluids in the lungs. If above than that, it might cause death. So leveraging on the nanostructures that we have, particularly in nanocat itself, there's many good candidates or materials that we can consider to be applied as a good gas sensors materials. I think typically it's a lot actually talking on zinc oxides, tin dioxide as well, and that's been very established in this part. And in this work, we're trying to see whether we can find a way to improve the sensitivities and also the response time of the ammonia gas sensors, and also to reduce the working temperatures, which most of the ammonia gas sensors nowadays, they are actually functioning at the higher temperatures. So these are the two research questions my team and I are working the past 1.5 years. So metal oxides, as I mentioned just now, is a big class of materials. Like these early mornings by Professor Jackie Yings, we actually have quite a handful of good materials to pick. But and it's against like what she says, it depends on your final applications. So as I shared just now, there's some new metal oxide which are rarely been reported in the literatures, and we selected this class of material that we call the molybdenum trioxides, MOO3s. And this class of materials possesses interesting characteristics such as high electrochemical activities. Low,
Dr. Ong, sorry for
yes,
disturbing.
yes,
May I know, are you actually moving your slide? Because
yes.
I can only see the front page of your slide right now. Oh, okay. Or else, can you please make it a single view so that it's easier to view maybe?
How about now? Can you see the full screen? No?
Not yet. Yes.
Maybe I
One
reshare
more time.
again.
Okay, thank you.
Okay. You can see now the slide?
I can see, but still not in a slideshow view.
This is when I click the slideshow view, it will disappear, right? Or what? Can I try again?
Okay, please.
You can see the full screen mode, right?
It's like it's not changing.
Maybe I
No,
reshare
it's not.
again. I close it and a moment.
Okay. Thank you.
Let me share again. How about now? Can you all see?
Still not in slideshow view, doctor. So maybe IT personnel can advise on this.
I have my slideshow views on my screen now.
Dr. Ong, and sorry for interrupting. I'm Nur Ain.
Yes.
While you click the share screen, right?
Alright.
Your share screen, can you select the entire screen? Entire
Okay.
screen.
I try again, sir.
Can you try again? Sorry.
Oh. Okay, how about now? Can see the slide now?
Can see the slide. Can you try to next slide?
Move around. Is it
Alright.
moving?
Now it's okay.
Okay, thank you. Okay, sorry for the accidents. Let's continue. Okay, this class of special materials, these are molybdenum trioxides. They have high electrochemical activities, low thermodynamic stability, and also the high specific surface areas. This is some of the important criteria for nanostructures when we wanted to decide whether it's suitable for sensitive sensing, particularly in this gas sensing materials considerations. So also this kind of material also come with a different structures. The first one is the orthorhombic alpha. We call it alpha molybdenum trioxide. We also have the monoclinic beta, and also the H, which is the hexagonal molybdenum trioxides. So, of course, we don't really go through all these individual one by one. And from the literature itself, it's giving good hints that the hexagonal types is the one that likely can do a better job. So, a student and I picked this class of these structures. And for the gas sensing process, I guess later on someone might ask what's the novelties. And there's a lot of gas sensing material right now is either is in two-dimensional thin film forms and some others embedded structures on the existing electronics platforms. And what we do over here is slightly difference is we are trying to taking advantages of the light traveling within the optical fibers. And then we're going to make the cladding, which is the coating material, outer coating material of these optical fibers, smaller. So we can give space to introduce this layer of green material, which is in this case is our hexagonal molybdenum trioxide materials. So we wanted to have these fiber optics to serve as our gas sensors. A few years back, another students, doctors, Dr. Akmal Yaya's students are working together with UPMs. She also working on the same platform, but is using a different materials. In her case, is the palladium and also zinc oxide combinations, but not sensing for gas, ammonia gas, but is for hydrogen gas sensing. And if you wanted to know more, you can check on the paper they published in IEEE Sensors Journal in 2019. So this is the structures of our sensors. All right, and it's a paper regions and how we deposit and how we introduce these metal oxides on this very tiny small fiber optics. Using a method that we call chemical bath depositions. We always have this belief in my research groups that we wanted to really not only make the nanostructures homogeneous, but the most important is that we have the ability actually to distribute or deposit it is much more larger scales rather than selective regions. I think this is one of the challenges that when we wanted to make a layer of nanomaterials on top of another substrate. So chemical bath deposition is a good technique that many established group out there also demonstrating the successful of depositing this class of material on different various substrates, but not fiber optic. Fiber optic is from our groups. Okay, the objective. We have two to share in the coming slide. Hopefully, it don't drag too long because I know you guys wanted to go off earlier, so I try my best to go a little bit faster. So only two. One is to design and synthesize the hexagonal molybdenum oxide nanostructures. Two approaches. One is we are using different precursors. As we all know that we might end up with the same metal oxide nanostructure at the end, but the way that we synthesize and also the type of material that we started to use, which is precursors to synthesize, will make a lot of difference on its final ultimate properties. Second one is to fabricate the room temperature optical sensors for the highly sensitive ammonia gas sensing. So we are using two types of precursors. In this case, this is the machines and the setups that we use to do the tapering process, which that thick layer of the fiber optics surface, we're going to taper it to make it thinner before that we coat the molybdenum trioxides in this case. To visualize the whole things, the A micrograph is showing the original fiber optics, and the B is the one that after the tapering. So it's a very tiny thing, but we don't want it to go beyond than that we actually broke the fiber optics. The setup for the chemical bath deposition is very straightforward. The bath itself will promote homogeneous heat distributions, which this is a very important characteristics if you wanted to really grow and deposit nanostructures on any kind of surface. In this case, it's fiber optics. The temperatures that we use is lesser than the 100 degrees Celsius, and the material that we make, we put it in another round of the heat treatments. We anneal it at the room temperature for 150s, just to get a better crystallinities and strengthen the structures and also the depositions adhesive between these two different materials. To test the gas sensing performance, this is the testing chambers, which will be locked and then will pass through the gas, and then when we delivers and apply the lights through the fiber optics sensors, and we get these all different sensing behaviors, which I'm going to share with you in a short while. As I mentioned just now, from the material synthesis point of view, we are using two different starting material, which is we normally refer to precursors and our molybdenum source. The first one at the left hand side is the ammonium heptamolybdate, and the right hand side is the sodium molybdate, which is chemical compound Na2MOO4. So it goes through the same processes. What's the difference is just the starting materials, and we're trying to compare them in terms of the morphologies, what type of structure that we get. I think more or less you can guess. Definitely we don't get the same morphologies by using two different precursor in this case. And also, what is the difference in terms of their chemicals and physical properties? 3DS, XRDs, TGA, the thermal, and also the FDIRs. And lastly, the UVVs on checking some of the band gaps, energies of this class of metal oxide materials. And we will select some of the good samples and then apply it for the gas sensing testing, which consists of dynamic testing, repeatability tests, and also the selectivity tests. Okay, two parts. So the slide with the blue is the part one, and slide with the light orange will be the part two. So let's start with the blue one. So this is the one that we use the ammonium heptamolybdate as a precursors. So as you can see, we make the thin films showing the nanograin light structures in the range between 40 to 70 nanometers. After annealing, it's getting slightly larger, which is ranging between 60 nanometer to 90 nanometers. In terms of the EDS mappings, on top of because silica dioxide is the outermost layer of the fiber optics. So we also have this MO and O mappings that is showing that only there's no other impurity involved except the fiber optic and also the molybdenum trioxide that we made. This can be further confirmed by the XRD and also the FTIRs, which the mapping itself is showing is the crystal planes of the hexagonal molybdenum trioxide faces, and also the FTIR showing the same. So in terms of the thermal properties from the TGAs and the first mass loss, this one is around 100 plus, is due to the desorption of the water molecules. And also when we hit between the 200 and also 250 degrees Celsius, it involved the elimination of the surface absorbed nitrate and also the ammonium ions. So if above 400, you have involved the decomposition of the internal structures. In terms of the UVVs itself, they have some slight change observations in terms of the band gaps, where the estimates hexagonal molybdenum trioxide, we have the band gap of 3.98 electron volts. Whereas after the heat treatments, we increase widen to 4.03 electron volts. So if you look at the gas testing properties, yes. Okay, both the untapped and also the tapped blanks optical fiber sensing properties, they are showing actually not much of the differences. And in terms of the sensing performance, using different concentrations, the 0.025 moles is the one that showing more significant absorptions compared to the rest that we picked. And in terms of the dynamic response, by adjusting the two different time durations, we are able to adjust the nanostructure growth on the tapped optical fibers. So the absorption response for the 30 minutes of the positions, we show a much more unstable result compared to the 20 minutes depositions. For the sensing performance between the different gas concentrations, we have the annealing of the hydrogen's hexagonal molybdenum trioxide materials will then increase the active sites on the material surface, which improves the sensing abilities. Same comparison between the S prepare and also the annealing samples in terms of their response and recovery times and sensitivity curves. In terms of the repeatability test, I think they are quite good, especially just showing small minor deviations. Can be talking about how sensitivity and also repeatables of this class of materials. We are not because at the times that we thought that the materials is also good for the other gases. So we also not only taking care of the ammonia gas, but we also going for the CS4, the methanes, and also the H2, the hydrogen gas testings. For the seconds of precursor that we use, which is the sodium molybdenate, we're getting a much more smaller hexagonal molybdenum trioxides, but this time is in nanorods morphologies. The size is around 14 to 20 nanometers thick. And again, after annealing, we foresee this become the diameter will increase, which we observe between the 23 to 37 nanometers thick. In terms of the EDX, we also will see some of the residues, sodiums elements on the coating layers on our depots, optical fibers. I'm not sure that whether this is the good impurity or something that is going to harden the gas sensing of the ammonia gas sensing using these precursors materials. Again, it's confirmed both for XRD and also the FDIR with the hexagonal molybdenum trioxides phases, both TGA and also UVs, giving the same observation like the previous precursors, but there's much more narrower band gap they observe in this case, which is for as prepared, we get 3.5 electron volts, where after the heat treatments, we get 3.7 electron volts. So the gas sensing performance itself, we only use the 0.1s in this case to coat dapper, and we find that the as prepared shows a relatively stable absorbance towards the 500 ppm to 5000 ppm of ammonium gas, which is around 0.1 to 0.15. So this absorbance unit. So it also showed a very small response of absorbance when only 100 ppm of ammonia gas is purged into the chambers. So I heard that sound. So let's go through the gas sensing mechanisms. So once you can see that the two different morphology has been made, although it's the same class of hexagonal molybdenum trioxides, and this is what we propose on its gas sensing abilities. So when the light is reflects in the depots regions, so the evanescence wave produced will directly interact and activates the metal's oxide thin films. When the sensor is placed at the ambient environment, the oxygen molecules will absorb on the metal oxides, absorbing sensors as oxygen wagons. So the chemosorption oxygen species will trap the free electrons at the conduction band near the surface areas through the following process. The free carrier absorption modify the optical band gaps, which relates to the interband transitions, leading to alterations of the evanescence wave at the interference of the sensing layer and the optical fibers. Thus, we believe that this will affect the transmittance of the lights propagate in the core regions. So if we found that it's ammonia gas atoms, molecules, is interact with in this case, it's a hexagonal molybdenum trioxide materials, and we'll see the changes in terms of the optical signals within the fiber optic itself. So as a conclusions, so the use of different material-based precursors will definitely result in different morphology growth of our materials. So by doing annealing heat treatments of our materials, it will help to improve the crystallinities, and this is also improve the material property to promote a faster sensing properties. So we thank the financial support from University Malaysia through the SATU research grants we obtained in 2019. And all the works that I share today is done by my master student, Mr. Chua Wen Hong. And his works is recently accepted. I think back last 2 weeks. If you want to know more about this work, you can go and find out from these newly accepted papers. So the currently my groups, the Advanced Functional Nanomaterial Research Groups under NanoCats, we still have a few openings. So if you all are interested to explore how we actually can use nanomaterials for different kind of application, not only gas sensing, our group also working on energy and also environmentals and also biomedical applications. Feel free just to drop me an email, or not just students, for any collaborators that we can leverage on a good networking session that we have in this first virtual conference. That's all. Thank you.
Thank you, Associate Professor Dr. Ong Boon Hong. Okay, it's so great to be able to hear your good sharing. So now we have one question for you from Dr. Nur Azrina Yusof. The question is, hi Dr. Ong Boon Hong. For repeatability testing, you use the same tapered fiber. How about the repeatability of the tapered fiber itself?
Yes, I didn't show the result over here. Is also showing a good repeatabilities.
Oh, so is that answering your question, Dr. Nur Azrina? And I also have one question for you, Doctor. Based on your morphology, you mentioned that nanograin structure has been successfully formed, right? So may I know how you differentiate actually the structure? How do you say that it is actually nano grain instead of nanoparticle maybe, or maybe based on crystal structuralities?
Yes, I think there's some debates on how to really classify or naming the nanostructures. If you go through a lot of SW's textbooks, I think they still have some room for debates. But in my case over here is because the purpose is very clear, because we wanted to try to make a different morphologies of this molybdenum trioxide. We want to really see that how morphology change is going to affect the gas sensing performance, and in this case, it's the ammonia gas sensings. So that's where Wen Hong and I is using two different precursors, so we get very different morphologies. So you can see that the second precursor is very obvious, is nanorod structures. Okay, so the first one is not in rod, but they are neither in irregular spherical shapes. So we just name it the nanograins because if you're talking about like nanograin or spherical type of nanostructures, these are the isotropic properties. So which means that regardless the orientation or directional property of your materials, you're going to get the same, in this case, optical properties. We are writing on the optical property of this metal oxide. But for one-dimensional nanostructure like nanorod, nanotubes, you have to really be careful because this is a material that very sensitive, not just their diameter, but also the how you arrange them in your application. But in this case, is the sensing. Any more other questions, Anani?
Okay, thank you for your answer. Yes, we have a lot of questions coming in. Seems like most of the participants are interested with your research topic. Okay, the second question comes from Mr. Aiman Sofi. The question is, hi Prof, does it give different results if using other type of optical fibers such as SMF, MMF?
The trend will be the same, but definitely we're not getting the same results. But maybe I shouldn't answer that because we haven't tried any other than fiber optics. But it's a good questions. You see that this also can open more research activities. If you are interested in these areas, we can also find times to work on this. Maybe I can add some things about why we wanted to make the gas sensing in this type of tedious structures. But why don't we just put on the two-dimensional, any flat substrate and all this, right? Because flat substrate type of gas sensing platform is the mainstream currently is in the commercial markets. And Wen Hong and I always wanted to challenge. We always think that can we apply the sensor in a much more extreme environment? Let's say that some places that we cannot really go in, and I think fiber optic is really good. You look at the bed of our sea now in the Pacific or whatever, it's all full of fiber optic. These are physical connection that helping supporting our information technologies. And if you can have, let's say, the fiber optics, no, can you surround in a very, very narrow type of space, either in your hydrogen gas, hydrogen cells, or your ammonia gas or production plant and all that things. So by supporting the ITO and also the future smart manufacturing, so these are good, every single small point sensors that are going to tell us that to prevent like the danger that I mentioned in my second slide just now. That's the main motivations to create much nightmare for mankind. If you have leakage of this, it might be a disaster. So this is where we're putting in this new fiber optics surface. Sorry, any other question again?
Okay, thank you. I hope it's answering your answer. It's answering your question, Mr. Aiman. Yes, last more question. Last one is from Miss Rabiatul Adawiyah. Hi, Dr. Ong Bung Hong. May I know which characterization is supposed to be done first in order to determine the optimum samples? Is it SRD, FESAM, or UV-Vis? Thank you.
There's two parts over here. First is the materials itself, and second part is on the gas sensing side. Right? Because to be frank, we try a lot. Not all the samples actually having that gas sensing abilities. So we don't report over here. So the first parts the optimization is we have to really get the distinctive different morphologies because our hypothesis is we wanted to see whether the different morphologies which leads to a different total surface to volumes ratios, which is one of the key parameters which means that if you have a higher surface to volume ratios, you likely to have much more sensitive sensing materials. So in our case is we have to go and quickly visualize and see first. So the FESAM is the first step on that. It doesn't really we can make any early conclusion by just looking at the FESAM itself. So in material science world, sometimes that we can make a very beautiful structures, but it doesn't guarantee that we can get a very good property out of it. And I think most of our students also will have this type of experience if you're working with nanomaterials. Sometimes the very ugly type of uncontrollable samples, the morphologies, but like they give you the best performance, and you have to crack your heads and have to do the reverse engineering to go and find out why this worked the best. I think the fundamentals, the science, and also the theory lying on a good sensing material is really on the active sites. Are you promoting the maximum active sites facet to your targeted gas? Or maybe these materials, you look at us, the molybdenum trioxide in this case, with these two morphologies, it doesn't really do well for hydrogen gas sensing, but it's working perfectly well for the ammonia gas in this case. So maybe you can talk more with Professor Amanda, the one that she shared this morning. You can go and using machine learning and find out what's the best structures, and then before you decide to really synthesize and fabricate and make one and prove that, see whether it really work for your targeted gas or not. There's still many other gas we need. We need more young people like you all to really work hard to find the material first, and later on you can commercialize it and let's grow and then proceed with our economy, knowledge economies that Malaysia always wanted to have. All right.
Okay, thank you so much, Doctor, for your great sharing. I believe that it gives a lot of inputs for all of us today. So thanks again.
Okay, welcome.
So now we reach at the end of the session. As announced earlier, we will have the best presenter for this session. Now I am very honored to announce the best presenter for session. This session goes to Dr. Nur Azrina Yusof. Congratulations, Dr. Nur Azrina Yusof. With the title today, a metal oxide biopolymer film as saturable absorber for Q-switch fiber laser generation at 1 micrometer wavelength region. So maybe Dr. Nur Azrina can contact organizer after this for further information. Congratulations again. So now we reach at the end of this session. Thank you for your participation. On behalf of MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form as given by session moderator in the full box. Okay, and hope to see you again tomorrow. Okay, thanks for all participate for all and see you again. Well done.
Thank you, Doctor.